Welcome to our video on molecular polarity. You were introduced to molecular polarity in grade 11 chemistry, where you use the method of vector addition to predict whether a molecule would be polar or nonpolar. We will be extending our understanding of molecular polarity this year and learning a new method that can help us predict whether a molecule will be polar or nonpolar. The polarity of a molecule is important because it determines what type of intermolecular forces will be present. And the intermolecular forces then determine the properties of a substance. And that is where we're leading to in this unit, looking at substances as a whole and examining their properties. We will be focused on the molecular polarity of small molecules with one central atom. However, we can extend this to large molecules, biomolecules, where there can be more than one region of polarity. There can be nonpolar regions of molecules and polar regions. Think fatty acids with the nonpolar tails and the polar heads. Let's now connect bond dipoles with molecular dipoles. Here we have a bent-shaped molecule similar to water. I've set the electronegativities so that atom B is more electronegative than atoms A and C. We can see the bond dipoles pointing in the direction of atom B, which indicates the electrons within those bonds are being pulled more closely to B. As a result of the unsymmetric shape and the two polar bonds, there is an overall molecular dipole. We see that yellow arrow there, and that is showing that the side of the molecule at the top, the B side of the molecule, is more negative than the A and C side. If we take a polar molecule and place it near an electric field, the molecule will orient itself so that the negative side is closer to the positive side of the electric field, and vice versa for the positive side. So let's put an electric field right here, and we see the molecule there has moved so that it's oriented so that like charges will attract. If I take this molecule and adjust it so that all electronegativities are equivalent, then there are going to be no polar bonds. If there's no polar bonds, the molecule itself will not be polar. And when we see if we apply an electric field, the molecule will not orient itself one way or another because there are no strong attractions there, no permanent dipoles. Let's now look at some real molecules. Here's SF4. SF4, when you work out the molecular shape, takes on an unsymmetrical tetrahedron shape, or a seesaw shape. In order to determine molecular polarity, our first step is to determine bond polarity. So here we're going to calculate the electronegativity difference between fluorine and sulfur. We need to calculate the electronegativity difference between each different pair of atoms within the molecule. In this case, the electronegativity difference between sulfur and fluorine is 1.4. Recall that the cutoff for a polar bond is 0.4. So if the electronegativity difference is greater than 0.4, we have polar bonds. If we have polar bonds, then we will label them as such. We'll draw vector arrows atop each bond, indicating that those bonds are polar, and as a result of the electrons all being pulled towards the fluorines, each fluorine end of the bond becomes negative, and the sulfur end of the bonds are more positive. Remember, these are partial charges, but they are permanent. In grade 11, you were introduced to the method of vector addition to determine whether a molecule is polar. However, vector addition becomes tricky with three-dimensional shapes and unsymmetrical three-dimensional shapes. An easier, and what I feel is more intuitive method, is to use the method of similar regions. Each molecule has a set of similar regions which we can compare, and if those regions are similar, then the molecule will not be polar. But if we do not have similar regions, we are likely to have a polar molecule. For molecules with a steric number of 5, like SF4, 5 pairs of electrons around the central atom, we want to consider 2 different similar regions. The first similar region is to compare the bonds on the axial positions, okay, above and below, the ones that are 180 degrees from each other. So think of that as a linear molecule within the larger molecule. And I'm just going to add the lone pair of electrons here just so we can picture where it would be sitting. Our second similar region is going to be the equatorial position, which is a trigonal planar. So first, let's look at the axial position. We have a sulfur-fluorine bond above, a sulfur-fluorine bond below. Those poles are going to cancel each other out, so there's no net pull of electrons above or below the molecule. However, then if we look at the equatorial trigonal planar, all regions here are not similar. We have 2 fluorines pulling electrons, making this side more negative, and here, those 2 electrons are just going to sit close to the sulfur. They're not being pulled out. Okay? As a result, we are going to end up with a polar molecule, and we would predict that the molecular dipole would be pulled towards the fluorine side of the molecule. Let's look at another example here. CH3F, a simple tetrahedral molecule. Can you take a moment right now and determine which bonds are polar and which bonds are nonpolar? Pause the video and determine that on your own. So in this molecule, there's one polar bond, the carbon-fluorine bond. Fluorine is more electronegative than carbon, and so the electrons within that bond are being pulled towards the fluorine side of the covalent bond. Now, depending on the periodic table you use, you may have found that the electronegativity difference between carbon and hydrogen is greater than 0.4. But recall that this is something that we just need to memorize, that we will always consider in this course the carbon-hydrogen bond to be nonpolar. Even though it's right near the cutoff, the carbon-hydrogen bond behaves as a nonpolar bond. Okay, it's so close that for all intensive purposes, we will consider it to be a nonpolar bond. So here, we have a symmetric molecule, the tetrahedral, with one polar bond. All regions of the polar molecule, the endpoints of the tetrahedron, are not similar. As a result, we are going to have a polar molecule in which the fluorine side is going to be more negative than the hydrogen side of the molecule. Okay, now that we've seen some examples, let's just recap the steps on how we determine molecular polarity. Our first step is to draw a Lewis diagram. Once we have the most likely Lewis structure, we'll use VSEPR theory to determine the shape and to draw a shape diagram. From the electronegativity values on your periodic table, you're going to determine and label the polar bonds. Then you compare similar regions to determine whether the molecule itself is polar or nonpolar. Let's look at one more example from question 9 in your worksheets to see how this works. Let's look at the ammonia molecule. NH3, when you work out the shape diagram, has a trigonal pyramidal shape. And once again, I'm going to draw the lone pair there, which sometimes we don't draw on shape diagrams, but sometimes it's helpful for determining molecular polarity. now I'm going to look at the electronegativity difference between each bond. Now all three bonds are the same, they're all nitrogen-hydrogen bonds, and you'll see that when you look at the electronegativity difference, nitrogen is more electronegative than hydrogen. So on each of these bonds, the electrons are being pulled towards the nitrogen. Since all those electrons are being pulled up towards the nitrogen, we are going to end up with a polar molecule. You'll see a pattern here that if we have an unsymmetrical molecule, okay, the molecule itself takes on an unsymmetrical shape, and then we have polar bonds with the molecule, it is usually going to be a polar molecule as well. And that's the case with this trigonal pyramidal shape.